Routing is one of the most fundamental mechanisms in computer networking. It is the process by which data packets travel from one network to another until they reach their destination. Understanding how routing works is essential for anyone entering the field of cybersecurity, because many attacks, misconfigurations, and vulnerabilities are directly related to how networks are interconnected and how traffic flows between them. Before diving into routing tables, it is important to recall a key concept from previous lessons. A network is a group of devices sharing the same address space, defined by an Internet Protocol address and a subnet mask. You have already worked with subnetting and CIDR notation, so you know that a /24 network contains 256 addresses, with 254 usable for hosts. When a device wants to communicate with another device on the same network, it does so directly. But when the destination is on a different network, it needs help from a router. A router is a network device that operates at layer 3 of the OC model, also known as the network layer. Its primary job is to forward packets from one network to another. A router has at least two network interfaces, each connected to a different network. When a packet arrives on one interface, the router reads the destination Internet Protocol address and decides where to send it next. This decision is made by consulting a routing table. A routing table is a data structure stored in the router's memory. It contains a list of known network destinations, and for each destination, it specifies how to reach it. Think of it as a postal sorting table. When a letter arrives, the worker checks the destination address, looks at the sorting list, and places the letter in the correct outgoing bin. Each entry in a routing table typically contains the following elements: the destination network, the network address and its prefix length, for example, 192.168.1.0 out of 24. The subnet mask or prefix length defines the scope of the network. The next hop, the Internet Protocol address of the next router to which the packet should be forwarded. The outgoing interface, the physical or logical port through which the packet should leave the router. The metric, a cost value used to choose between multiple routes to the same destination. Lower is usually better. Let us walk through a concrete example. Imagine a simple network with two routers, Router A and Router B. Router A has two interfaces. Interface 1 connected to the network 192.168.1.0 out of 24, local office network. Interface 2 connected to the network 10.0.0.0.0 out of 30, a link between the two routers. Router B has two interfaces. Interface 1 connected to the network 10.0.0.0 out of 30, the same link. Interface 2 connected to the network 172.16.0.0 out of 24, a remote office network. If a device on the 192.168.1.0 out of 24 network wants to reach a device on the 172.16.0.0 out of 24 network, it sends the packet to its default gateway, which is Router A. Router A looks at its routing table and finds that to reach 172.16.0.0 out of 24, it must forward the packet to the next hop, which is Router B's address on the 10.0.0.0 out of 30 link. Router B receives the packet, looks at its own routing table, and sees that 172.16.0.0 out of 24 is directly connected to its second interface, so it delivers the packet. This chain of forwarding decisions is the essence of routing. There are two main categories of routes that appear in a routing table: static routes and dynamic routes. Static routes are manually configured by a network administrator. They do not change unless someone modifies them by hand. They are simple, predictable, and consume no bandwidth for updates, but they do not adapt to network changes automatically. If Router B goes offline and there is no alternative path, packets will simply be dropped because the static route still points to an unreachable destination. Static routes are commonly used in small networks or for very specific routing policies. Dynamic routes are learned automatically by the router using routing protocols. These protocols allow routers to communicate with each other, share information about the networks they know, and update their routing tables accordingly. Common routing protocols include Routing Information Protocol, which uses hop count as its metric, Open Shortest Path First, which uses link cost and creates a complete map of the network, and Border Gateway Protocol, which is used between large autonomous systems on the Internet. In a dynamic environment, if a link fails, routers can detect this and reroute traffic through an alternative path without human intervention. One special type of route deserves particular attention: the default route. A default route, often written as 0.0.0.0.0, or sometimes called the gateway of last resort, matches any destination that is not explicitly listed in the routing table. When a router or end device does not know where to send a packet, it uses the default route. For end-user devices, the default route points to their local gateway, typically a home router or corporate firewall. For routers deeper in the network, the default route usually points toward the internet or a higher-level router. Without a default route, packets to unknown destinations would be silently dropped. Let us look at an example of what a simplified routing table might look like on router A. Destination: 192.168.1.0 out of 24. Next hop: directly connected, interface, eth0, destination, 10.0.0.0 out of 30. Next hop: directly connected, interface, eth1, destination, 172.16.0.0 out of 24. Next hop: 10.0.0.2, interface, eth1, destination, 0.0.0.0 out of 0. Next hop: 10.0.0.2, interface, eth1. In this table, the first two entries are for directly connected networks. The third entry is a static or dynamically learned route to the remote office. The fourth entry is the default route, which catches all other traffic and sends it toward router B. When a router receives a packet, it performs what is called a longest prefix match. This means the router selects the routing table entry with the most specific, longest, matching prefix for the destination address. For example, if a packet is destined for 192.168.1.55, the router compares this against all entries. The entry 192.168.1.0 out of 24 matches and has a prefix length of 24 bits. The default route 0.0.0.0 out of 0 also matches but has a prefix length of 0 bits. The router chooses the more specific entry, which is 192.168.1.0 out of 24, and forwards the packet accordingly. This longest prefix match rule is critical and is what makes routing both precise and scalable. From a cybersecurity perspective, routing is not just a theoretical concept. Attackers can exploit misconfigured routing tables, inject false routes through poorly secured routing protocols, or perform route hijacking to intercept traffic. A technique called BGP hijacking, for instance, involves announcing false routes to redirect internet traffic through an attacker-controlled path. Even in penetration testing, understanding routing helps you map the target network, identify segments, understand where firewalls and access controls are placed, and determine which paths traffic takes so you can plan your approach accordingly. When using tools like Wireshark, which you have already practiced, routing behavior is often visible in captured traffic. For example, you can observe time to live, TTL, values in Internet Protocol headers decreasing as packets pass through routers. Each router decrements the TTL by 1. When TTL reaches 0, the packet is discarded and an error message is sent back. This mechanism prevents packets from circulating infinitely in case of a routing loop. Tools like Traceroute exploit this behavior to map the path a packet takes from source to destination, making it valuable for network reconnaissance. To summarize the key points covered in this lesson, a router operates at layer 3 and forwards packets between different networks. A routing table contains destination networks, next hops, outgoing interfaces, and metrics. Static routes are manually configured and do not adapt automatically to changes. Dynamic routes are learned via routing protocols and can adapt to network changes. The default route, 0.0.0.0 out of 0, handles traffic to unknown destinations. The longest prefix match rule determines which routing table entry is used. Routing misconfigurations and protocol vulnerabilities are real attack vectors in cybersecurity. Understanding routing is essential for network reconnaissance and penetration testing. Mastering these concepts gives you the foundation needed to understand how traffic flows across networks, how segmentation works, and how to think like both a network defender and an attacker when analyzing or testing a target environment.